So I'll be telling you something about Unidentified sounds. I'll give you an intro on how to discriminate between different species, which you're going to be doing later on with baby whales. And so this is just a little bit of an overview if you ever have to do it otherwise. So Unidentifieds have various acoustic signals, one of which are echolocation clicks, and you can, I guess I'm not coming for it, there it is. So you can see those vertical, you can see those vertical lines here, those are the echolocation clicks. And you can even see something down here, the time, well I should probably explain, you have a frequency axis here, time axis on the X, and the color denotes amplitude. And down here, and this would be a spectrogram, down here you have a time series with the amplitude on the y-axis, and again time on the same time axis on the x-axis. And you can see here that there are those pulses coming in, and some of them appear pretty regular. So you would imagine that this, and that signal comes from the same animal. And likely it's going to be turning its directed echolocation beam towards the receiver, it's at the receiver, and then away again. Just by looking at the amplitude. So it's basically kind of scanning and sweeping over the receiver. Now, as they scan and sweep, those echolocation clicks change dramatically. And this is a recent publication by Woodall and others. And he measured in the vertical and in the horizontal axis how an echolocation click changes. And so you're going to have here spectra showing the amplitude over the frequency, and above that, a time series with the amplitude over time. And so you can see this is a direct, straightforward click. It is a strong impulse, and then it kind of wiggles out. It's fairly short, and it has a very broad, fairly clean spectra here. Now, as you go more to the sides, and that is the same vertically as horizontally, I mean it's not the same, but it is a similar thing, you're going to get a distorted spectra that is much more narrow and likely much lower in frequency. And then the time series, on the other hand, seems to be expanding, and that is much more pronounced as you look at the horizontal axis.
Is this the same click?
That's the exact same click, measured just in various areas around the vocalizing animal. So I'm showing this to demonstrate that you can't just measure a single click and then you get it down, you know this is it, and that's what the species does. The single click measured from different aspects is going to be looking a lot different.
Do you have left and right as well?
They have, yes, that comes on top of that. And I'm not going to go any deeper into this. There's a lot to say just to that. Then they also produce, as you likely know, whistles and something called buzzes or burst pulses, depending on the context in which these signals are being produced. So over here, that tonal thing is a whistle, and then these rapid clicks, really, that are lined up very quickly one after the other, that are perceived tonally, are then termed buzzes or burst pulses. Now, I brought an example of two different behavioral states. One is where the animal is foraging, so they have a series of echolocation clicks, well, I guess we can look here, very irregularly spaced, and at some point, they're going to, as they approach a target, they're going to reduce their inter-click interval, what John already introduced, until it gets so short that we perceive it as a tonal. And that would be called a buzz. I hope that this works. Let's see. I don't think I hear anything. So it would be a buzz, kind of thing like that. We did test it, yeah, but
Oh, got it.
it's fine. It's not critical.
Try the other side and see if it's just a...
I don't think. Oh. Well, I'm sure most of you have heard it. So a whistle is modular like that, right? And when you hear a buzz, it's really kind of a zzz, pulses. And here you can just see down there in the example where the animal is bow riding, this is a communicative use of this type of signal, most likely, where it's mixed from whistles that are grading into buzzes and grading into whistles, and it's a different use of this signal. Now, we want to look at the SoCal species and see what kind of signal they do produce. And I'm primarily going to look at the echolocation side of things. We are going to be seeing signals differentiating these more common species here in Southern California. Most of you probably know how sperm whales look like. They are at pretty low frequencies down here, usually not a whole lot higher than 20 kilohertz. And they have about 1 second interclick interval, so they're very regular. And it sounds kind of like knocking on wood.
Try it and see if this...
I can, but that's as much of an acoustic input that I'm going to have anyway for this stage. Then these are, so sperm whales are pretty easy, just because they're really low in frequency. Now, Pacific white-sided dolphins and Rizzo's dolphin, Melissus olivia and others have found that they're actually quite nice to discriminate as well. If you have only one single click, it's, like I said earlier, not as easy just because of the different things that can happen to it. But when you have a series of clicks, then you can see there's a 1 hour of time period displayed here. Then you can see that these have some sort of a stripiness to it. And depending on where, here for example, you have 1, 2, 3, 4 stripes up to 40 kilohertz, and here you have 1, 2, 3, 1, 2, 3 stripes. And so this is already telling you, is it Rizzo's or is it Pacific white-sided? And then there are 2 types of Pacific white-sided, potentially genetically distinct. We haven't been able to test that hypothesis thoroughly yet. And they have just slightly different banding patterns.
Can you point to the 4 stripes again?
So you have 1, 2, 3, 4 over here.
There's no 5 up there?
Well, you could probably, but if you're looking just up till the 40 kilohertz, then yeah. And oftentimes you don't see as nice of an example where you would have that strong of a signal up high. And then the difference is up to 40, here you have only 3. So that's easy enough. Bottlenose and common dolphins, in comparison, they do not have anything like that. This is an example of short-beaked, long-beaked, common dolphin together with bottlenose dolphin, and they just look absolutely undistinguishable. And to this point, we haven't really managed to change that. Also, automatic classifiers haven't been too successful in taking care of that. What we can say, though, for example, if you're out in the field with your total hydrophone array, and you haven't had a sighting yet, but you see some acoustics coming up, then usually common dolphins appear in very, very large numbers of, well, definitely a whole lot larger numbers in a group than, say, bottlenose dolphins. And just by sheer numbers, here, for example, you can see it's full and full and full of whistles, and this is zoomed into that area. So and clicks for that matter. So this must be a very large group of animals. So you can assume that that's a common dolphin group. Now, killer whales, they also echolocate. You can see here again the echolocation clicks. And those usually reach down to, say, 10 kilohertz or so a little bit lower than, for example, our common dolphins, which are more like the 20 kilohertz, the lower end of it. So those are distinctly lower. And additionally, they also have other signals that are quite distinct, and we're going to zoom into that more now. So killer whales produce something that is called pulsed calls and also whistles. And those pulsed calls basically consist, as with these here, they have kind of a 500-ish, what we call fundamental, so the basis, the lowest line would be maybe around 500 hertz or so. And then you have multiples of that fundamental being then the harmonics of that signal. And they are not a tonal signal, so it's not a consistent waveform at a certain frequency, but it's not echolocation, it's distinct pulses that are so rapidly produced, kind of like the buzzes that we saw earlier, that we perceive them again as a tonal signal. Versus whistles like this one here, where you don't see such a strong increase in that area, dense like these here, which would be a tonal signal. And then additionally, killer whales produce something that is called what we call a high frequency modulated signal. It's questionable still what the purpose of that signal is, whether it's a communicative signal or not, but it ranges from about 40 kilohertz down to maybe 15, and it has a fairly regular repetition of about, well, once every 2 seconds or so. So those are very distinct signals that you can definitely distinguish and find for killer whales. Then of special concern in the past have been now beaked whales, Cepheidae, and common for SoCal would be cuviers and to some extent Bear's beaked whales, and then possible in the area a range of other species. And up till very recently, we were not able to say what kind of sounds those different species do. Until about 2005, 2006, when people published really nice papers of tagged animals. This is an example of a blainville's beaked whale, and this over here is an example of a bottlenose dolphin. So you can see here the bottlenose dolphin, similar to the clip that I showed earlier, has a strong onset, sharp onset, and then kind of trails off. Now beaked whales have kind of a slight increase in the time series and then a slight decrease again. And as they increase and decrease, additionally, they also sweep over frequencies. The frequency rises over time. Most delphinids, or all delphinids that I can tell, do not have that. So that's something beaked whales seem to be uniquely having. Now, additionally to that, we and others have found that you can discriminate those beaked whale species, not only that they do have a sweep, but also by the general frequency range that sweep occurs. And those are the 5 species that we currently can discriminate in the Southern California bight. And besides the sweep frequency range, there's also how fast that sweep is going to happen, so the sweep rate, the duration in that regard, the duration of their pulse, and very important, they seem to be having a species-specific interclick interval. So you can see up here I say, or interpulse interval, if you want to call it a frequency modulated pulse. Here the IPI would be 230, 510, 300, 480. So this is not a random number, that seems to be specific for the species, and combined with the other aspects, you can tell them apart pretty easily.
How many animals for each of these did you average these over, or is this just one animal?
Oh, no. This is, I can't tell you numbers of animals, of encounters that we have, and those would probably be in the order of 10,000s of clicks. Then there are signals that they have criteria do not match anything that we know of that we can put a tag on. And I put them into groups, so we have a 40, 43, 50, and 70 kilohertz peak frequency signal. And they appear in SoCal, maybe Gulf of California, and a little bit to Central California. And those could fit very well with some of the species that we don't know of, like pygmy, beaked whale, hobs, beaked whale, ginkgo-tooth beaked whale, and so on. Right, so I think I have, do I have a little bit of time for?
Yeah.
Yeah, so I don't know if there are any questions further to what I just showed. Yeah.
Interclake interval or pulse interval was brought up earlier. Are there any other species? I know Baird's or Blainville is useful for that, but are there any other species in SoCal that can be used as a
discriminatory factor?
Exactly.
Most of the delphinids seem to be very flexible in the use of the interclake interval. Additionally, most of the delphinids appear in such large numbers that it is hard to pull out individuals to trace that interclake interval.
Are the sounds produced by these animals modulated or altered by either the environment or the proximity of other individuals of the same species?
So they're definitely altered by the environment, yes. Which has to then do with the propagation of the click. So since they're very broadband, obviously the lower part of the frequencies are going to be less more altered than the higher part as a function of distance. In terms of altered...
I mean more of the propagation, excuse me. In other words, the sounds they produce, at 1 meter, do they change the way they produce sounds in regards to
Yes.
the environment or other individuals nearby?
Yes,
frequency shift or something like that?
I have observed at Palmyra Atoll where there's a very strong diel pattern from day to night. I've observed that the animals are producing sort of they're having sort of a Lombard effect, it seems, where they produce stronger amplitude clicks at night versus day, which seems to be shifting the frequency higher overall, which can either be due to that extra noise or it could be due to a behavioral adaptation because they're during the day more likely resting while they're foraging at night. And it could also be that they might be altering their echolocation click dependent on what prey type they're going for. So they are fairly flexible in what they're doing.
I guess what I was getting at is in the inverse, if you're trying to identify an organism
Yes.
that the sounds that they make vary in regards to these other factors, what's that range of variability, and does it preclude you from being able to discriminate one species from another?
So yes, and that's why there are only a number of species that we can to this point confidently discriminate. But then there's a large group of dolphins where you can't at this point. Who knows? Maybe we'll find out. Yep.
When you were pointing out the bands earlier, when you were looking at the like the Grampus spectrogram, what you were talking about being the bands in there look pretty much like they're formant bands or something like
Right.
that. You feel that it's pretty stable among or within a species, but then there are going to be subtle changes among individuals. Has that sort of been your guess or experience?
Well, so for those strong bandings that we see for Grampus and Pacific white-sided, that probably has strongly something to do with the anatomy of the skull. Like you say, formant would be the corresponding thing likely for human species. In what extent individuals differ from each other, we haven't really tested that. But what we do know is that there are geographic differences within Grampus, for example, that those three bands have the same structure. If you look at them and compare them, they do look alike, but the frequencies are slightly different in different regions. But it's consistent within the region.